Okay, so in this video we're going to calculate the potential difference between the two inner surfaces of a coaxial cable. And coaxial cable is the same stuff that cable television runs on. So hopefully that gives you a visual. And because we're looking at an ideal Gaussian distribution, we can go ahead and use the simpler form of our potential equation. So we're going to start with delta V is equal to minus the integral from a to b of E dot ds. Now, we don't know what E is, so we have to find it. And to find E, we have to turn to Gauss's law, because we chose the Gaussian distribution. Had we chosen the Coulomb distribution, or Coulomb's law way of doing it, then we would have had to have used that equation. So we're going to use Gauss's law, and we get the integral of E dot dA is equal to Q enclosed over epsilon naught. And E is going to be constant everywhere inside our along our Gaussian surface. And so we'll just put our Gaussian surface somewhere inside of our coaxial cable. And whenever we integrate delta V, it's going to go, the Gaussian surface will stretch from the inner surface to the outer surface. Okay, so E times, now the integral of dA becomes the wrapper of our soup can, so this becomes 2 pi r times L is equal to Q enclosed, which we can write as lambda L over epsilon naught. And L cancels out here, and so we get E is equal to lambda over 2 pi epsilon naught r. Now remember, typically lambda is not something, well, I shouldn't say typically, but on the AP exam, lambda may not be something which is given, so don't be afraid to write this as Q over L. And if that's going to be the case, then we'll write Q over 2 pi L epsilon naught times R. So we'll substitute these values back into the original equation, and we get delta V is equal to minus the integral from, now A is going to be RA and B is going to be RB, and I just left, I don't have the subscript R there. I'm going to leave those as A and B, so it's still A to B. E is now going to become lambda over 2 pi epsilon naught R, and this is all going to be integrated with respect to R, dr. So basically everything here is a constant, and we get delta V is equal to minus lambda over 2 pi epsilon naught times the integral from A to B of dr over R. So delta V is going to be equal to minus lambda over 2 pi epsilon naught, and the integral of 1 over r becomes the natural log of r. So we get ln of r evaluated from A to B. And so this whole expression now becomes delta V is equal to minus lambda over 2 pi epsilon naught times natural log of B over A. And that is our final expression for finding the potential between the two surfaces of coaxial cable. Now, if you wanted to, you can get rid of the negative sign here by switching A and B. Remember that that's one of the log rules, and basically what we have with that log rule is the natural log of A over B is going to be equal to minus the natural log of b over a. So those are going to switch.